Hello, everyone. I'm Mariana Potcoava from the University of Illinois at Chicago, and I'm honored to present the paper, Light-Sheet Fluorescence Microscopy Using Incoherent Light Detection. Thank you for organizing and hosting this fantastic event. This work was done in collaboration with Professor Myung's group from the Northern Arizona University. I'll start with the motivation of our research, going through the light sheet and lattice light sheet systems. After that, I'll introduce the incoherent holography lattice light sheet system called ILS with high numerical aperture and low numerical aperture. I'll cover the results section using three techniques: the conventional lattice light sheet, ILS 1L, which is the incoherent version of the lattice light sheet with one diffractive lens, and ILS 2L with two diffractive lenses for imaging polystyrene beads as well as biological samples. In conclusion, in light sheet microscopy, the excitation plane or the light sheet is created by focusing a Gaussian intensity profile laser beam in one dimension using a cylindrical lens as illustrated here. The advantages of light sheet instruments are the optical sectioning capability, speed, and low photobleaching or phototoxicity for biological samples. However, in conventional light sheet microscopy, we face fundamental drawback between the size of the beam and the axial resolution. Therefore, a thin and long light sheet cannot be created with a Gaussian intensity profile laser beam. The specific lattice beam shaping of lattice light sheet microscope overcomes this limitation. At UIC, we use a home-built lattice light sheet instrument for neuroscience and all type of single-cell imaging research. Lattice light sheet microscopy was developed by Eric Betzik at Genelia Research Campus. Cylindrical lenses stretch and collimate the beam to form a sheet projected onto a binary special light modulator with the acronym SLM. SLM generates an optical lattice of Bessel beams. An optical lattice is a periodic pattern of non-diffractive beams. Annular mask acts as zero-order filter, removing artifacts and lengthening the sheet. Particular pattern is created in the backfocal plane of the excitation objective that results in a lattice on an array of non-diffractive beams parallel to each other in the sample plane. Galvo mirrors deter the sheet in X and sweep in Z. The Z Galvo synchronizes with the Z piezo, which is the objective, to scan an object in 3D. Lattice light sheet is an ideal technique for fast, low-intensity, high-resolution cellular imaging, but the drawback is that the 3D scanning is done by moving the detection objective or the sample stage, which, of course, and it has a small field of view, which is ideal for subcellular imaging of a single cell or cluster of cells. Therefore, we thought of a different modality of how to perform 3D imaging without moving the detection objective and how to expand the field of view. So I'll go to the ILS version of the conventional lattice light sheet, but before that, I would like to cover a few words about optical lattices. Optical lattices can be designed for various wavelengths, diffraction, mask, annuli, single or multi-Bessel beams. The spacing between each pair of Bessel beams can be also adjusted to balance the confinement and the thickness of the lattice. Here in the upper row of this slide, the upper row shows the optical lattice generated with high numerical aperture, and the bottom row shows the optical lattice generated by the lower numerical aperture annulus. We can see that the lower numerical aperture beam has a Gaussian-like shape. The sheet is deterred X direction with a galvo mirror to create a uniform light sheet. The lattice light sheet with incoherent detection and Finch approach overcome the limitation of moving the detection objective or the sample stage, and also the limitation of having that small field of view. I will say a big thank you to Professor Rosen and his group for developing this technique for the incoherent light. In Finch, the spherical beam coming from an object is split by a phase SLM, which is different than the phase SLM in the conventional path, in the conventional lattice light sheet system, which is a monochrome special light modulator. So the beam is split by this phase SLM into two spherical beams with different radii of curvature. Finch uses a few combinations of diffractive elements displayed on the SLM. Here we use two configurations. We call the first configuration ILS 1L that uses one diffractive lens and a constant phase mask with shared pixels. We use this technique for calibration and alignment purposes. So basically this ILS 1L is the incoherent version of the conventional lattice light sheet detection path. The second technique, called ILS 2L, uses two diffractive lenses of different focal lengths with randomly selected pixels. This configuration is used for holographic imaging and gives the freedom to choose only one polarizer in the system and not two, to create the interference between the two beams, which implies that lower doses of light could be used to image biological samples. Lattice light sheet, the conventional lattice light sheet, and ILS 1L use the same scanning geometry where the Z galvo mirror synchronizes with the Z piezo objective to scan the sample in 3D. In ILS 2L, the detection objective is kept fixed, while the Z galvo moves in Z direction to increase the visibility of the Fresnel patterns at certain depths. For imaging calibration, we used 500 nanometer fluorescent beads for the excitation wavelength 488 nanometers. We performed the same experiments using the conventional lattice light sheet and the ILS 1L, both systems with lower numerical aperture, where the Z galvo was stepped in 0.1 micrometer increments through the focal plane of the detection objective, which was simultaneously moved the same distance with the Z piezo controller for a displacement range of 40 micrometers for scanning area of 208 by 208 micrometers squared. We noticed that the beads outside of the 78 by 78 micrometer squared area, green square here, for lower numerical aperture cannot be detected. For the higher numerical aperture case, this area is at best 52 by 52 micrometers squared. The ILS 1L could perform better than lattice light sheet, but the resolution is lower in the axial direction due to the blurring effect of one of the lenses that is focused to infinity. But our incoherent system enables full complex amplitude modulation of the emitted light for extended field of view and depth. This set of images was obtained using the ILS 2L, where only the Z galvo was moved above and below the reference focus position of the objective, which corresponds to the middle of the camera field of view, which is located in each frame over here in the middle of the field of view. In increments of 10 micrometers in the range plus minus 40 micrometers. The two wavefronts from the SLM interfere with each other at the camera plane to create Fresnel holograms. 4 interference patterns were created using a phase shifting technique, and further combined mathematically to obtain the complex amplitude of the object point at the camera plane. The image in the right lower corner shows the max projection of all z-planes where the beads were found. We observe that ILS2L performs better in comparison to the conventional lattice light-sheet system in deterring mode regarding the scanning detection area. The scanned area with detected beads in ILS2L system with lower numerical aperture is the full field of view of the CMOS detector, while the scanned area with detected beads in a lattice light-sheet system with lower numerical aperture is about 78 by 78 micrometers squared. In terms of axial resolution, we already showed in the Optics Express manuscript that the axial resolution of the ILS2L is higher than that of lattice light-sheet because the objects are localized with greater precision using diffraction. I have a few slides of biological sample images. These are obtained with higher numerical aperture, not with lower numerical aperture. So we are working on this experiment. We are in the middle of the experiments. We finished the bead scanning, but we have to now to do the biological sample images. Here it's an example of imaging done on lamprey spinal cord ventral horn neurons that have dendrites that are sufficiently large to cover the whole camera field of view of 208 by 208 micrometers squared. What we'll see here using the ILS2L, the max projection for only 3 reconstructed amplitude or phase images and superposition of all 3 could give similar results as the lattice light-sheet and within a larger resolved sample area. Here it's an example of deformation measurements of neuronal excitability. A neuron was filled with dye, and the osmolarity of the superfusate was altered by adding water to cause a change in volume. The analysis indicates that the technique can resolve sub-micrometer size changes in these images over here. Another experiment, we performed colocalization of 2 dyes by labeling a lamprey motor neuron with dextran conjugated to Alexa 555 and Alexa 488 and applied 24 hours prior to the experiment by injection into the lamprey motor neuron muscles. Again, we can notice that the ILS technique is superior to the conventional lattice light-sheet technique by achieving bigger Z-scanning range within a larger resolved sample area. In addition to the amplitude images, the ILS2L can provide access to the reconstructed phase information. In summary, we show that ILS imaging using longer but lower resolution beams is functional. We achieve maximal field of view of the detector, which is 208 by 208 micrometers squared. ILS2L provides a better method for finding the focal position than the conventional lattice light-sheet, which is the glass optics system. We performed 3D imaging without moving the sample stage or the detection objective. But of course, there is a drawback with the method. So as I specify, we fix the detection objective in the middle of the field of view. And because of that, we have to modulate the laser power and the exposure time in the z-axis. So lower exposure time and lower power in the middle of the field of view, and higher exposure time and higher laser power in the at the edges outside of the plus 40 micrometer Zigalvo range. Thank you for your attention, and thanks again for the opportunity to be part of the conference.